Okay, so we'd like to find the Laplace transform of our Dirac delta function, and really more generally of our Dirac delta function at any spot, right? So that impulse, here's our t-axis. That impulse could come out here at t0. It doesn't have to be at 0, so we just have t minus t0 like that. And so the way we'll do it, though, is we'll go back to d tau, and we'll look at the Laplace transform of d tau of t minus t0, because that we can do. I'm not sure how to do the Dirac delta exactly without doing the limit first. And so this is by definition our integral from 0 to infinity of e to the minus st d tau t minus t0 dt. Now though, and I'm going to use the way I define it, the 1 over tau for a length of tau, and so this can just reduce to 0 to tau of e to the minus st d tau t minus t0. Your textbook, of course, uses the interval from minus tau to plus tau, but well, their proof is actually a little wrong in the text. They miss a negative, but they miss it twice, so it ends up working out just fine. But so we have this. Now, on this interval, 0 to tau, oops, I didn't want 0 to tau. I kind of messed it. Right, we're centered at t0, so I want this to be t0 to, well, t0 plus tau, so I'll just do it that way. Right, t0 to t0 plus tau. On that interval, this function just has a height of 1 over tau, so it's a constant, and we can factor that out. So that's 1 over tau, t0 plus tau, e to the minus st dt. Okay, so, right, that just had a constant value of 1 over tau. Factor that out, and it's 0. It was 0 everywhere else, so that's why we got down to this interval. And now this, I can do this antiderivative. So the antiderivative of this will be a minus 1 over s e to the negative st. Okay, so I'm going to write this as minus 1 over s tau. I've got my 1 over s there, negative 1 over s, e to the minus st from t0 to t plus tau. And this is where your textbook messed up. They did not have that negative sign right there. But, like I say, they sort of fixed it in the end, because then they didn't take care of the negative later, as we will do. So t0 plus tau there. And so now we put that in, so this is minus 1 over s tau, the upper bound, so e to the minus s t0, and then we'll have e to the minus s tau. Okay, so that's that upper bound, and I just separated out the two pieces after I multiplied by s. And then minus e to the minus s t0, like that. All right, so we can factor out e to the minus s t0. And what we have left, we've got this negative here, so I'm going to put that back in, so I'm going to make that term positive. So e to the minus s, oops, well, let's just fix this. I'll go down a little bit. So e to the minus st0. I could use the eraser up there, but this seemed quicker. Right, so I factored that out. So I've got a minus 1, but I'm going to put this minus with it, so it's a plus 1. And then here I have a minus e to the minus s tau for this term here. Okay, and that's all divided by the s tau. And so that's what I get for this Laplace transform of d tau of t minus t0. Okay, now let's take the limit of that. Well, if I take the limit as tau goes to 0, notice, that this term doesn't have a tau in it, so it's just a constant term. It gets factored out. So I'm just going to look at the limit of this part. So the limit of 1 minus e to the minus s tau over s tau. Well, 1, if I just plug in tau, I get 1 minus 1, so I get 0, but on the bottom I get 0. 0 over 0, that looks like a good time to use L'Hopital's rule. So this is the limit as tau goes to 0 of, take the derivative of the top, and I get s e to the minus s tau divided by the derivative of the bottom with respect to tau, so I just get s. Whoops, there it goes again. Okay, and this is by L'Hopital. I always think it's a good idea to make sure you point that out when you take derivatives of tops and bottoms separately like that. So this is L'Hopital's rule. Now those s's, of course, factor those out. The limit is 1, doesn't matter. I just plug in. Now I can just plug in tau, and I see that I get e to the 0 or 1. Okay, so that limit is 1, and so that means that the limit of that part is 1, and so we just get this part left over here when we actually do that limit, and we want the Laplace transform of the Dirac delta function, t minus t0, that ends up being e to the minus s t0. And so notice if t0 equals 0, you get 1. Right? So Laplace transform of Dirac delta function at 0 is equal to 1. So there's the derivation of our Laplace transform for the Dirac delta function. We get that. And so now I guess we're ready to solve some differential equations. So we'll do that.